So what I was just displaying and talking about was the cyclization event, the cyclization of monosaccharides. Monosaccharides, well, I would say sugars in general are going to be most stable and most commonly found as a cyclic form. Now, pentoses and hexoses readily undergo intramolecular cyclization. So they go from the linear to the cyclic form. The former carbonyl carbon becomes what's known as, or becomes a new chiral center, and this is known as the anomeric carbon. So a question that I always like to ask is, does a linear sugar have an anomeric carbon? No, it does not, because carbon number 1 on linear glucose is not a chiral center. Now, when the former carbonyl oxygen becomes a hydroxyl group, the position of this group is going to, determine if the anomer is an alpha or a beta designation. So if the hydroxyl group, this is what I was just talking about, if the hydroxyl group is on the opposite side of the ring as the CH2OH, which is carbon number 6, or we saw it as carbon number 6 on glucose, the configuration is alpha. Now, if they're on the same side and cis, that would be your beta designation. Now, the cyclization of our monosaccharides ultimately goes into this sort of one of these two different forms, basically. A 6-membered oxygen-containing ring is known as a pyranose. So this is named after the pyran ring structure. A 5-membered oxygen-containing ring is called a furanose, and this is after the furan structure. So pyran and furan. The anomeric carbon is usually drawn on the right-hand side, so generally that ends up being your carbon number 1, or in the case of a ketose, again, we're thinking about this as a new chiral center. Well, when you cyclize a ketose, well, keep in mind, carbon 2 is the one that contains your is your carbonyl carbon. That goes from not being a chiral center to being a chiral center. So an anomeric is C2 for a ketose. Okay. Now, here are some examples of different sugars. So we've got alpha D glucopyranose. Now, what I would recommend doing is thinking back to what was our structure for our D glucose. We didn't care about carbon 1. We didn't care about carbon 5. We didn't care about carbon 6. We focused only on carbon 2, 3, and 4. 1, 5, and 6 we didn't really need to worry about. Okay. Now for 2, 3, and 4 we had a system, RLR. Oxygen on the right-hand side, left-hand side, right-hand side. That was our system that we used to basically keep in mind the naming. Now, we can do the exact same thing when we're talking about a cyclic sugar. The only difference is, the way that I always treat this is down, up, down. So carbon number 2, the hydroxide is down. Carbon number 3, the hydroxide is up. Carbon 4, the hydroxide is down. Okay, so there's our quick look at glucopyranose, specifically alpha D-glucopyranose. Beta D-glucopyranose. Now let's again look at carbons 2, 3, and 4. RLR becomes DUD. Down, up, down. Okay, now that indicates that we're still talking about glucose, but what we're looking at as our difference here is, and what we want to recognize as our difference here is carbon number 1 for an alpha D sugar versus carbon number 1 for a beta D glucopyranose. Okay, so next up is we want to look at, just a second, the cyclization of fructose, which, if you remember, fructose was presented as the ketose glucose And for this, we only had to worry about carbons 3 and carbon 4, C3 and C4. Now, if you remember, for carbon 3 and carbon 4, it was a left-right designation. Now, let's look at the cyclization that has taken place to make fructopyranose. We want to look at carbons 3 and carbon 4. Carbon 3 and carbon 4. Left corresponds to up, right corresponds to down. So does this follow? It does. Okay. The difference between these two sugars is not, well, they're both fructose, but we've got alpha D versus beta D. Okay. So our newly formed hydroxide group, where is that positioned? Well, if that hydroxide group is in the opposite orientation of our CH2OH, which is carbon number 6, well then that is an alpha D sugar. If it's in the same positioning, well then that is a beta sugar. So one of the things that people regularly have questions about is, well, I understand a D sugar, I understand an L sugar, kind of. Well, I want to go ahead and show you D-glucose, linear glucose, versus L-glucose, linear. Now we've got 1, 2, 3, 4, 5, and 6. CH2OH. We've got a hydrogen, oxygen, and then RLR. Oh, yeah, so I've got, let me go ahead and look at carbon number 5, hydroxide group on the right-hand side to indicate that I'm looking at a D sugar, and then RLR. That's my way of remembering where my hydroxide groups are. And we're golden. Okay, so there is D-glucose. Now, L-glucose. I'm going to draw the exact same structure, but I'm going to, that's 5, CH2OH. Okay, I've got there. L, okay. I've got to draw my hydroxide group on the right-hand side, the left-hand side of my penultimate carbon. That's carbon number 5. Now, how do I know that I'm going to draw L-glucose? Well, the important thing that you have to keep in mind is this is a non-superimposable mirror image. Okay, so what you would do is think about this in terms of like relative. So carbon number 2 and carbon number, oh, that should be an H. Sorry about that. Carbon number 2 and carbon number 5, they're going to both have a hydroxide group on the right-hand side. Carbon number 3 is going to be on the opposite side, and carbon number 4 is the same side. Okay, so there's one way that you could think about a D sugar. Well, if you flip the hydroxide group, that means you flip everything else because it's a mirror image. So H, H, OH, H, OH, H. Okay, so essentially, here's our plane. Here is these two carbons mirroring. These two carbons mirroring. Yeah, I drew enough. These two carbons mirroring. I didn't really draw this particularly well or anything like that. But if you flip carbon number 5, you got to do everything else. Otherwise, you're not drawing glucose. Okay? I hope that makes sense. So this shows D-glucose versus L-glucose. Now, naturally, a question that people always have is, well, what if I cyclize it? How do I draw the cyclic form of D-glucopyranose? And I'm not going to worry about alpha versus beta right now. I'm just going to draw my general structure, CH2OH, O, and I just want to show you how I draw glucose. Down, up, down. Okay, so naturally a question is, well, what if I want to draw L-glucopyranose? And I can't remember exactly in this textbook, but it's actually pretty uncommon to find a representation of the L-glucopyranose or L any cyclic sugar, and I think that largely just focuses on their biological relevance. Well, what you're going to be doing is you're going to flip everything. So this right here, we've got our CH2. It goes into the ring. Carbon number 5, hydroxide group is up. Hydroxide group on 4 is down, and 3 is up. There is L-glucopyranose. Now, here, what I've drawn up top, this is beta D-glucopyranose. Now, if I go ahead and draw this right here, this is an alpha alpha L-glucopyranose. So what I want you to take away from this are a couple of different things. One, what's the difference between alpha and beta? Then, what's the difference between D and L? It's much easier to visualize D versus L sugars when you're talking about the linear forms of them. It's a little bit more complicated whenever you're talking about the cyclic forms of them. However, it's important to recognize that, can you have an L cyclic sugar? Absolutely. Do you form a new chiral center? Absolutely. But what are the implications of this? Well, this OH group here, these are both positioned upward. But again, you've got to put them relative, or you have to, for proper nomenclature, you have to visualize that with respect to CH2OH. All right.